This one in particular, it's at a beautiful venue. Pretty much everybody's staying in the hotel here. And so that means, after the sessions, people are going out and getting a beer and continuing the conversation. And it's just a great way to experience the conference.
Please come on in, take seats. To talk on performance, the closer you seat, the better the performance is. Also, performance, the observation itself, the data is what it is, but what do you do with this is subjective, depends on your point of view. I want to demonstrate the importance of the point of view. I need 2 volunteers from the audience. 2 people from the audience, please, come on up here. 1, okay, we can stand here. And someone else on the other side, please. Just face each other. Okay, you can come closer to me. Do you see the arrow? Okay, which way is it pointing? Okay, there is some disagreement on this subject. So everybody sees what they're seeing. I'll also show it on screen. Does everybody see the arrow? Which way is it pointing? All right, now you can observe this one, everybody else observe the screen. I'm going to flip the arrow. Which way? Okay, so you see the difference the point of view makes. All right, well, now we can start with the talk. Well, thank you for coming. Let's talk about performance in C++. Well, if you program in C++, you're probably interested in performance. That's usually one of the reasons. It'll be a specific area of performance optimizations. If you want more information about performance, in particular about C++ from me, I have these 2 books. The one on the right, The Art of Writing Efficient Programs, just came out, and the publisher sent me a discount code for conference participants, so I'll share that. Let's go straight into the talk. What's our plan for the next hour? We're going to talk about what constitutes, what allows good performance, and in particular about using the hardware capabilities efficiently, because the better you use the hardware resources, the more computing you can do with it. We'll focus on the conditional code and branches, and then I'll show you the optimizations of branches, including branchless programming, which sounds like removing the branches, which is what it is. Toward the end, you'll see the actual benchmarks, just to kind of set you up for what kind of results could be expected. The first line is some very common code, and let me point at it. A very common code in this function here. There is a very simple equivalent transformation that speeds it up, well, on this machine by about 3x. Here is another very common code Again, there is a very simple transformation that speeds it up by more than 3x, and I'll show you the full code and the benchmark and everything. But this is the kind of thing that you can expect when these optimizations really work. So, what do the branchless optimizations fundamentally owe their efficiency to? It's the idea that modern hardware is very capable. It can do a lot of stuff, computing hardware, and your performance, well, first of all, there is an algorithm, so get the result you want with minimal work. Second, there is the efficient use of language, don't do any work that you don't need done. And then there is, okay, you now have certain amount of computing to do, you have the computing resources of your processor and other computing capabilities. You want to use all of these resources, all of the time ideally, to get through the computations that you need done. What do the processors have? This is actually a pretty old one, but still, there aren't simple like additions, multiplications. They have to do a lot of other stuff to get the results back. So the execution units themselves, there are actually a lot of them, and they aren't even the biggest part of the silicon. There is other stuff there. Pretty much every block of this diagram can be used more efficiently with certain optimization techniques, and you would have to find the book on performance. I talk about it in my book. There are, of course, others. We're going to focus on the execution units. Very simple code. So we have some arrays, or maybe vectors, whatever there are sequences, and we're doing some repetitive computation in a loop. So this loads up the CPU here, but the truth is, it's a very inefficient use of the CPU. It doesn't load up much of it. What it does is still actually pretty complex. You have some data in memory, the CPU needs them in registers. So first, we load the data. Second, we load more data. Then we actually do the operation like multiplication, and that gets us the result. We're doing one multiplication per data per iteration. That's very inefficient as far as CPU is concerned. If you ask the CPU to do 2 multiplications or multiplication and addition or division, it'll do that in exactly the same time. So this code and the previous code would run on most high-performance CPUs, like on x86 CPUs, would run on ARMs, would run at the same time. So you get the second operation basically for free. But that's actually not the limit. Depending on what CPU you have, you can fit in a lot more, and you can write benchmarks like this to see on your particular CPU just how much more you can stuff into it. A lot, somewhere between 5 and 10 easily. And that's before we get to specialized hardware units like vectorized units, which have their own math components completely separate from the general arithmetic units. Now, this all sounds very good, so I have computations, and I'll just have my CPU do all of them at once. That's great. The problem is, you almost never can do that because you have data dependencies. In order to do the next computation, you have to have the results of the previous computation, which means all of these compute units basically wait for one of them to complete, then the result goes to the next one, which does the next operation, and so on and so forth. That's the data dependency. Things can get even worse if you have code dependency. So you may have branches, conditions, and now not only the CPU must wait to execute some instructions because it doesn't have the data to do it, it also doesn't know which instruction has to be executed until it computes that result. There wouldn't be much point in putting so much compute power on a single processor if we didn't have some workaround for these problems. So let's start with data dependency. Data dependency workaround provided by clever CPU designers who came up with the idea of the pipeline. What does the pipeline do? Well, we have our iteration of the loop. So we can do some operations on the data that we have, let's say for V1 and V2 for a particular iteration. So we can do addition and multiplication. Well, there is also the product in that same iteration. We can't do it yet because we don't have the results of addition and multiplication. What can we do in the same time? The multiplier unit is just sitting there. It's available. What could we do with it? We could do the multiplication from the previous iteration. So if we're adding and subtracting the array elements for some value of I, we could be at the same time multiplying the results of the addition and multiplication for I minus 1. So this is how the pipeline works. We have identified in our computation a stream of instructions that has a data dependency within the stream, so the instructions are ordered. But there are two separate streams, and they're interleaved, so there is no data dependency that between them at any given moment of time. So we can add elements I minus 1 while we're multiplying the elements I minus 2 and so on. Any questions on the pipeline? Any questions? Could you turn on the mic, please? Just come closer.
Why are the results of -1 and -2, the expressions there, not a data dependency for the multiplication that needs them?
Okay, the question was why are the results for -1 and -2 not a data dependency for the multiplication? They are, but not for the same iteration. So the addition for minus 1 is a data dependency for multiplication for I minus 1. But it's not a data dependency for multiplication for I minus 2.
Why is the computation of I minus 1 not a data dependency for accessing that index?
Oh, I see, okay. Yeah, so there probably is another round of the pipeline where i's are incremented, but in reality increment is coded into the instructions. So, so yeah, there is another kind of another train of instructions where it starts from 0 and computes in some register it computes the value of 1. Then if it needs a register to index, it will compute a value of 2 in another register while keeping the value of 1. So now you have two streams of instruction. 1, 2, 1 goes to 3, 2 goes to 4, and as many as it needs to hold the parallel streams. There are some tricks in hardware, I'm oversimplifying, there are some tricks in hardware to actually optimize indexing, but that's basically there. If you didn't, it would just cost you 2 more streams in the pipeline. Any more questions? Okay, so that's the pipeline. The result of the pipelining is that basically the entire pipeline is busy doing parallel streams of execution. And the end goal of it is to increase the CPU utilization. Ideally, we would have all of the CPU compute units doing something and not waiting for anybody's data. And if the pipeline is wide enough, you may be even able to do that. So far so good until we get to conditional code. So we handled basically data-dependent data by just waiting for this data to be computed while doing something else. Now we have the problem that we don't know what to do. Until we know the result of, let's say, this comparison, what's greater, V1 or V2, we don't even know what's the next instruction. So this is the bane of all pipelines. Now you have to wait. Conditional instructions take a while to actually get you the answer. You have to wait and you don't know what to put in the pipeline, so you create bubbles in the pipeline during which you do nothing. This negates our wonderful achievement of fully loading the CPU with computations. Now, in truth, this isn't 100% accurate. The CPU can do some conditional operations in a single operation without jumping. We're going to set that aside. In my code, I'll use simple conditional operations. So if you see some conditional operation that in your compiler is replaced by cmove or something like that, just ignore it, pretend it isn't. There are some limited things compilers and processors can do to avoid certain branches. I'm showing you the examples that may be optimized. Just if you know that in your compiler it's optimized, just ignore it and go with it. You can get more complex stuff that isn't optimized. Even if that condition thing was optimized, our loop actually has a hidden conditional that should ruin our pipeline to begin with, and that is this wonderful pipeline goes with I plus 1, I plus 2, and so on, only if I plus 2 was valid in the first place. There is a condition there for I less than n at the end of the loop. So we shouldn't have been able to do our pipelining at all, and what I told you should not be possible. Because before starting the third stream of instruction, we actually have to check if I plus 2 is even valid. There is, of course, an antidote to that problem as well, again, courtesy of CPU designers. And what they do is, for this loop, it's something very natural. It would be a great shame to lose all the benefits of the pipeline for a long loop where the failure of the condition occurs exactly once at the end. You know, we would have to pay for the possibility that I is greater than n for like a loop of size of, I don't know, millions, when in reality there is only one of those. So what do? They make a guess. The processor itself, not the compiler, the processor, makes a guess about which way the condition will evaluate. And in case of the loop, one branch, which is the condition you're in the loop, I is less than n, the processor very quickly will figure out that that's what usually happens. So it's going to assume that it'll keep happening. And the other branch, the one that exits the loop, will just be idle. Now, again, very important, this is not the compiler thing. Your source code and your machine code look exactly like the written with the loop. The machine code also has the loop. What your processor executes looks like this, with loop being effectively unrolled. So it's hardware unrolling. It has nothing to do with the compiler. Compiler may decide to unroll some loops. It has nothing to do with that. This is hardware loop unrolling. As soon as the hardware unrolled the loop, it immediately pipelines it, and we're back to what we already figured out about keeping the CPU loaded. Now, if your machine code looks like a loop, and your hardware unrolls it, how does it work? In your machine code, we say, load v sub I into, I don't know, EIX, load v2 into EBX, do the add, and then the next iteration again, it's the same machine code. So again, EIX, EBX, but they're busy. They're busy for the first stream, and you're telling it to use them for the second stream. How does that work? Well, it works like this. EIX doesn't mean EIX. In reality, CPU has physical registers, whose names you normally don't know, and the conceptual registers, which are what we used to know about, let's say, x86, RCX, EBX, all of those. And there is a mapping between the logical names and the physical names. There are a lot more physical registers than logical registers. So if you see EIX being used twice in this hardware unrolled loop, it's not the same one. It's called register aliasing. So that lets the hardware pipeline work. Okay. Any questions on the successful prediction and pipelining? Yes, Pablo.
If the hardware is speculatively going through the more expected conditions, how does it avoid faulting onto it?
Okay, next slide. The question was, what happens if the guess resulted in some catastrophic fault? We'll get there. Any other questions? No? Online? No? Okay. So, so far we're assuming that the guess is successful, so what did we get? Pipeline relies on continuous stream of known instructions. They're fetched, decoded, and executed in parallel. Conditional branches disrupt this great ability because we don't know what to fetch and execute. CPU just assumes that it knows. So all the gray stuff will pretend that it's not even there. So instead of saying jump is true, we'll just say jump and execute immediately the next instruction. Now we can pipeline. Okay, that's if all of it works. The success of this critically depends on how good you can predict the future. As long as your future is 100% accurately predicted, you're fine. You could pretend that jump, if true, is really jump. What happens if you are wrong? If you're wrong, the first problem is you're not going to find out for a while. When you're going to find out, you need to do several things. Everything you computed, you need to throw away. You need to start the other branch, load up those instructions, and get them to run. Okay, that's expensive, but there is an even bigger problem. Anything that you've done speculatively has to be discarded. What if you've done something that cannot be undone? Well, what could that be? Here is a very common prediction. If P is not null, dereference P. P is almost never null. What does the processor do? The processor says, oh, look, it's almost never null. Let's pretend it's never null. That's our prediction for the future. And the next thing it does is dereferences P. What happens if P was null? It still dereferences P. So what happens is any errors that happen in speculative execution must be somehow held suspended. They'll become real and be reported if the evaluation of the condition confirms that the speculative branch should have been taken. Otherwise, they just have to be disappeared. If a particular error cannot be handled in this way, you can't proceed with the speculative evaluation. You have to stop and wait for reality to catch up with your guesses. Another interesting thing is, there is one thing that absolutely cannot be undone, and that's writes into memory. Once you write into memory, the old content is gone. So writes must be held. CPUs have write buffers exactly for that purpose. And the write buffers are basically, you can call them registers, they're buffers, sitting between the processor and the memory, and that's where the values are queued up until confirmation comes in that, yeah, condition was indeed what we guessed, now we can commit. Did I answer your question? Okay. Now, the bottom line is the process for recovering from that mess is really, really expensive. Which means you really don't want to guess wrong. Well, how do we guess? Basically, fundamentally, it's predicting the future based on the past. It's actually not that trivial. They're pretty smart. But fundamentally, it's predicting the future based on the past. So this is going to be the loop itself is going to be very easily predictable. It's a long loop. Predicting that it's going to continue as a loop is a good bet. At the end, it'll be a pipeline flash, but it'll be amortized over many, many iterations. So that's going to be a good prediction. The one inside the loop, now that's where it gets interesting. If that Boolean is always false or always true, it's going to be well predicted. If it varies, well, depends on how predictably it varies. I'm going to be using the Google benchmark and the standard perf profiler on Linux. You can use VTune or whatever profiler you want. The capabilities that I'm going to show you are not exotic. And the benchmark, again, any benchmark will do with what I'm about to do. Let's see some code. I'll just show you the difference. Okay, is the code visible? Yeah, okay. So before I show the code, any questions on what I sort of promised to prove to you? I'm going to now prove it with code, but is it clear what I set up to prove? Any questions on that? So far, yes, question?
I think it would be good to just reiterate it again.
Okay, so what I set up to prove is that the pipelining will improve the utilization of the hardware and therefore give you better performance. And the CPU will figure out a way around the data dependency that is present in code like this and pipeline. And if there is a branch, in which case it can't pipeline because it doesn't know what instructions come next, if it can predict it, it will still pipeline successfully. And if it can't, you'll pay a huge penalty in performance. So that's what I set up to prove to you. And then, of course, next thing is I'll show you how to optimize so the huge penalty doesn't happen. All right, so by the way, we're talking about predicting by the processor. One thing we must absolutely avoid when doing these tests is predicting by the compiler. And compilers are damn clever. Well, almost damn clever. In particular, no compiler that I know knows that rand returns positive values. So this defeats every, so the one on the left is always true. This defeats every compiler I know. They basically, they do not optimize at compile time, even though it actually could be optimized. You really don't want compile time optimizations to happen here when you want them to happen in a real program. You don't want them to happen when you're doing the experiment. So the difference is going to be, one of them is always true, and the other one is randomly true and false, more or less randomly. Otherwise, they're doing exactly the same work. Well, let's see what happens. The one that was predicted on this machine, it's running on this laptop, about 1.2 billion iterations per second. 1/6 of that. That's the cost of constantly mispredicting the branch. Right there. So half the time, whatever the predictor did, roughly half the time on that branch, it had to recover from a false prediction. Flush the pipeline. If it did a write into the wrong place, it has to flush the buffers and then load up the instructions that should have been done and execute those. Takes time. All right, now in this case you actually know why it's so slow, because we started from the code and then we figured out that like one of them might be slow and we confirmed it. What if it was a real program and you didn't know? So if we started from the slow version, didn't have any idea about why it's slow, how would we figure out where to get to the fast version? We need to know, we need to somehow find out where the branch misprediction happens. So now I'm going to show you how to profile for this. And again, I'll be using perf. And I'll just run perf stat, which will tell me the average profile for the entire program. So it'll tell me, well, I'll show you what it'll tell me. So what it tells me is, for the entire program, I executed this many instructions, I had this many cycles, and so on. In particular, the interesting bit is here. 10% of all branches were mispredicted in that entire program. Now, this includes the branch at the end of the loop, which is almost always predicted, and whatever other branches, like the benchmark itself, has set up. So this is for everything. This tells you that you have a lot of 10%, a lot of misprediction, doesn't tell you where. In our case, it's easy to find out where. In general, you would ask it to generate annotated source or annotated assembly, and it would show you the line in the code where the branch mispredictions are. I'm not going to show that just in the interest of time, but if you want to just come see me after the talk and I'll show you. It just takes a little while to actually set it up and run and get into the menus. Now, 10% of all branches were mispredicted. Is it good? Is it a lot? Or is it not? I mean, we don't know what 10% means. Well, let's see what the good program does. Less than 0.1%. 10% is a lot. You keep doing these experiments, you get some experience for it. 10% is really bad. 1% is actually pretty bad. And the reason it's even 1% is bad is because the mispredictions are really, really expensive. So even 1% of those, but each of them is very long. Any questions on this basic example where I have shown you the cost of misprediction? Yes?
Is the cost of a misprediction worse than if you did 5 predictions?
Well, first of all, I can't disable it in general. Well, okay, that's not entirely true, but the ways to disable it require like severely messing with the CPU. If you keep generating interrupts all the time, you will keep resetting the history. Now, this is actually an interesting question. How much time? Okay, I'll answer. In this case, the answer is probably yes, and we can get some data on it because one of the CPU vendors made an embarrassing mistake at one point in history and made their branch predictor always do the exact opposite of what they should have done. And the performance of that particular CPU could be increased by almost an order of magnitude if you kept hitting it with interrupts as fast as you can. True story. Okay, so summarizing our results, some small fraction of a percent of branch misses is good, 10% really bad. Now, it's very important to point out that even though I have shown you that, yeah, the mispredictions are expensive, you always have to make sure that you really have those. Mispredictions are expensive. Misguided optimizations are also expensive. You have to know that you have the mispredictions. You have to measure every time. And I'll show you actually the example why. So let me show you the next example. And the next example is going to be something very similar. Again, this code is the same. The only difference is the conditions. I'm starting from random true or false, and then I'm going to alternate every time. So it's going to be true, false, true, false, true, false. Now, if we think that CPU predicts based on the last one, it's going to get it wrong every time. If we think that the CPU predicts based on some average, it's going to just be confused and not know what to do because 50% is one way, 50% is the other way. Well, let's see what it actually does. I'll run with perfstat immediately. First of all, it was slower than the fastest one, but much faster than the slow one. And second, the misprediction rate is, as you can see, still less than 0.1%. What the CPU predictor figured out that pattern. It figured out the alternating pattern strictly based on the history and predicted that every other one is true, false, and what phase it's in. So do not try to predict what the CPU predictor is going to do. While it is pretty good about guessing the future, we aren't. So you have to always do these measurements. Any questions so far? Sorry? The code.
We do have a few online questions.
All right, let's do online questions.
So the first one is, who made the drawings?
There will be my sister-in-law, but there will be acknowledgement at the end.
Okay. And then a couple questions about the likely and unlikely attributes.
Okay, so the question was about likely, unlikely. Let me explain what they're talking about. Most compilers have built-ins, and so basically there is a way for you to put like a prediction on the conditional that will translate into some hardware thing that will guide the CPU predictor towards certain decision. What exactly it does varies by the hardware, like would you completely override the predictor and just force it, or if you're always wrong. I mean, usually if you're always wrong, it's going to be pretty bad. Now, the problem with those is, in reality, programmers are really much worse at guessing the future than they think they are. You have to benchmark your code to see how good you are about it. It always pays off in trivial cases. So you have like, debug asserts. So they're saying, like, if this condition is false, just abort. Well, A, you hope that it doesn't happen that often. And B, you don't really care how slow abort is. So yeah, put the predict false, like the abort is not going to happen on that. It's going to make that assert, which hopefully is never going to fire, is going to make it much cheaper. A well-predicted branch is very inexpensive. So if you're very sure, yes, they can pay off. In any non-trivial case, the odds of you getting it wrong are high, unfortunately.
Do side channel and branch prediction exploit mitigations of the recent years?
Okay, the question was about side channel and exploits based on speculative execution. So this is basically the question about Spectre, Meltdown, and all their friends. I have a whole section in my book on that. It's long. It would take the rest of this talk for me to tell you, how it works and what it does. Yes, the speculative execution, which is supposed to be completely undone, leaves very subtle traces that can be observed. That's the fundamental issue with this. I'll leave it at that. I can explain, you'll find me after the talk, and I'll explain, if you want, all the details, including the working code.
So the question specifically was, do the mitigations that have been put in place against those, do they mess with the pipeline optimizations?
Maybe. So, the mitigations vary depending on which of these, like so Spectre 1, Spectre 2. Some of them don't mess with anything unless you actually try. So some of them, basically, if you're not trying to do a real exploit, don't do anything for you. So I can show you the code which runs in presence of Spectre 1 mitigations that actually would still do Spectre 1 on the data that you have legitimate access to, but just not accessing. So that doesn't hurt anything, and so it depends on which exactly vulnerability you're trying to exploit. And which of the preventions we're talking about. So some of them do, some of them don't. Any more?
Yeah, there are a few more. Do you want me to continue?
Let's see, where are we on time? Okay, let me go a little forward, and then we'll try to pick up more questions. Any questions in the audience? Okay, please. Okay, that's what I'm going to show you next. So, in general, if there is like a simple, basically, if there is a way to deduce what it's going to be, the hardware is going to do it for you, so you won't even see it. So if you see it show up on the profiler, the question was basically, okay, the profiler ran, showed you something, what do you do next? So if there is a way for the CPU to predict it, which means if you can optimize without destroying that branch, the CPU will handle it. So if it shows up on the profiler, messing with the branch is probably not going to help you. You have to do something pretty drastic, which is why I'm saying these optimizations are invasive. You have to be sure that you need them, which means you have to run that profiler. So now I'll show you the invasive optimizations. So, well, we talked about this. You have to measure, you have to confirm with the profiler. All right, let's look at several cases. Now, there are lots of these variations. I'll show you kind of the basic types of it, and then you can apply them in a lot of similar situations in your code. Here is a very common one. And that gets us to the point of usage question. So if X or Y, then do something, otherwise do something else. Here is how I, as a programmer, look at this. There is a condition. If it's true, I do it, otherwise I don't. That's not what the compiler sees, that's not what the processor sees. They both see it totally differently. What they see is X is one condition. If it's true, we take the true branch. If it's false, we look at Y, and if that is true, we take the true branch. And if they're both false, then we take the false branch. What's the subtle difference? The subtle difference is, I think of it as, or a programmer think of it as, there is one condition, X or Y. The processor thinks of it as two conditions, which means if the branch taken is predictable, but how you get there is not, you think that this is a predictable condition. Your processor disagrees with you 100% because it thinks that it's not a predictable condition, because it's half the time it's X that got you there and half the time it's Y that got you there. And the comparisons must be done separate. The checks, the tests for X, if X equal true and if Y equal true, must be done separately, because the logical OR is defined with a short circuit execution, which means if X was true, we don't even look at Y. This is very important. It gets you do things like the reference pointers that could be null and you don't get there because the previous condition prevents you from happening, but it may have a cost. So I'll show you the cost. Same body of the loop again I have, but now I have two branches. So there are two Boolean values here, and this is how I initialize them. So if one of them is true, the other one is always false. So I'm basically, I'm demonstrating you the worst case. Now in the best case, everything is always true, everything is predictable, predicted branch is very cheap. So then it's not interesting. The profiler will show you that nothing bad happened, you're good. I'm teaching you about optimization, so I'm going to show you the worst case. And the worst case is you always get into the true branch, but you have 50% chance of getting there through X or through Y. Same 10% of mispredictions, and the total rate was still about 200 million operations per second, which it's the same loop, so you should be running at over 1 billion if everything is perfectly pipelined. So because of the short circuit, the processor has to evaluate X, predict the result, which is a fundamental failure, it's random. Depending on the result, jump to evaluating Y or not evaluating Y, predict the result again, which is another fundamental failure because Y is also random. So two branch mispredictions, if X was false, one branch misprediction on X, if X was true, and then you go do the computation. The annoying part of this is, the result is actually well predicted. You always go into the true branch. You're paying for nothing. There should be a way to figure out that the whole thing evaluates to true without hitting the two mispredictions along the way. Yes?
Would it help if we used bitwise OR?
Next slide. Okay, so what can you do? Well, some people try to put a temporary variable. Utter failure, let me tell you right away. Two reasons. One, still needs to do the short-circuited evaluation. Two, the compiler is really good at eliminating those. It'll undo your temporary variable. So don't even try. What does work is replacing short-circuited logic evaluation with something that doesn't have a short circuit. If we're dealing with Booleans, which are 0 and 1s, additions or multiplications for end can handle that part, or bitwise logic can also handle that part. Now, this actually works. Well, let's see if it works. The only difference is plus versus logical OR. Very few mispredictions, not quite as fast as our fastest loop, but we do more work there. There are 2 conditions to evaluate. Much faster than the one that was plagued by bad mispredictions. So yes, it worked. It got the mispredictions down, and it became much faster. Now, the kind of main danger here is some compilers in some of these loops will figure out that you're really trying to do a logical OR and will helpfully optimize it for you and generate a logical OR in the code. Yes?
Why doesn't the optimizer go the other direction and say, if the logical OR, there are no side effects, always make it a bit?
It could in very specific cases. So, why doesn't the optimizer replace logical OR with like bitwise OR or whatever? Well, first of all, it needs to know that your bools are true bools. Because remember, 3 is true. Doing a bitwise, or 2 is true. Doing a bitwise OR between 2 and 1, I mean, gets you 3, but doing the AND doesn't get you anything. So doing the OR works, doing the AND doesn't. So 1 is that has to know that they're actually Booleans. 2, it could only do that without your consent if basically the execution cannot fail. So if you're doing star P, you may be sure that the pointers are never null. It can't, in general. And 3, it doesn't always work, which actually doesn't necessarily stop the compiler from doing it. But it is an optimization you have to confirm, and I'll demonstrate. Any other questions before I confirm? Yes?
It looks like the total number of branches decreased in your second panel.
I replaced 2 branches by 1.
But the perf says that you have 4 branches.
It's per second,
Please
so
repeat
it's...
the question.
What happened to the total number of branches? Remember, these are per second, so I'm running faster. I'm taking more branches per second.
What are the left? 1.8 billion versus 1 billion?
This is the good one, the optimized one, and this is the non-optimized one. So yes, I'm doing more branches per second because I'm running the computation a lot faster. Yes, so the second from the bottom is branches per second. The one on the bottom is percentage of all branches that were mispredicted. So I'm doing a lot more branches per second. I'm actually doing a lot more instructions per second in general, right? Let's see, do I have instructions? Yeah, so I was doing 0.78 instructions per second. Now I'm doing 2.41 instructions per second. And some of those are branches. So I'm just doing more instructions a lot more instructions per second, including the branches per second. That's a good thing. And I'm mispredicting much fewer of them. So I replaced 2 branches by 1 because instead of checking separately X and Y, I'm checking the result. Now, if the result was also random, this would not have paid off at all. So if the overall result was 50% you go into the true branch and 50% you go into the false branch, you would still have that misprediction, and this would not have paid off at all. The reason it pays off is that the total result is fairly well predictable. In this case, it's perfectly predictable, but the way you get there isn't. So I'm removing the mispredictions on the way to get to a very predictable result. That's the optimization. Worked great. If the total result is predictable. Any more questions? All right, well, let's get to the next of it. All right. Now, there is one other thing that we could notice in this particular optimization, and that is that there is a cost in removing that branch. And the cost is we are doing more work. The short-circuited evaluation, which had the condition, spared us from evaluating y half the time. In doing that, in replacing it with plus or bitwise OR, we're reading x, reading y, and doing the bitwise OR or plus every time, regardless of the outcome. So we are doing more work on the CPU. So that's the trade-off. Now, it is actually very general. Typically replacing branches with any of the optimizations that I've shown you or will show you results in doing more work. Why is that okay? Why was it faster? The reason it's okay is because CPU has a lot of spare computing capability. You can slot in 1 or 2 adds almost all the time for free. Those units were sitting idle anyway. So you can get, if you can get 1 or 2 adds to evaluate along with what you're already doing, that isn't going to cost you anything. Most of the time. Not always true, but most of the time. Because typically you're nowhere close to loading the CPU 100%. It's just really hard to do. Now, this is important to you if your metric of performance is the throughput. How much can I compute, or how fast can I finish the computation? If your metric of performance is how quickly the battery drains, you probably don't want to do that and run unnecessary computations through that processor. So now you have a trade-off to make. But we're talking about throughput for now. So optimizing branches away typically results in more work. Often, but not always, you can fit that work into computation capabilities that would have been idle otherwise. Not always true. Which means, again, you have to measure that you're gaining. You do this optimization, you have to measure that you're gaining. In particular, if x and y were very complex expressions themselves, you probably would not have gained if you had to evaluate both of them all the time. All right, let me show you one more optimization because, so I've shown you one for different branches, for short-circuited expressions, applies to question colon and other things. I'll show you one more that is kind of fundamental of the other type of common branchless optimizations. We went from 2 branches to 1, and we saw that it was good. What's better than 1? 0. Going from 2 branches to 1 and then to 0 branches, that should be even better. The fundamental trick there is always the same. And it's basically, this is on the slide. Everything else is syntactic sugar around it. You use booleans, or conditionals, as indices into an array. So instead of returning conditionally expression 1, or instead of returning a result, I don't mean returning from a function, instead of computing the result conditionally as expression 1 or expression 2, you compute both of them, put them in the array, and fetch the right element of the array using the index operator. Removes the conditions, costs you unconditional computation of both expressions. If the expressions are short, and the branch was poorly predicted, you often win. If the branch was well predicted, you always lose. If the expressions are long enough, you have to measure. I'll show you the example, and that'll be all that we have time for, but I'll show you the example of that. So this is a branchless optimization. The code is, the result of the computation is exactly the same. The branchless optimization on the left, I just take the branch. On the right, I put both the results into an array and choose one using the index. The branch itself is going to be mispredicted. It's random. This is where I determine the condition. So this is going to be mispredicted badly. That's the branch version. That's the branchless version. What, 4 times? Something like that. Faster. So branchless version is faster, even though I'm computing 2 expressions. Now, if the branch was perfectly predictable, so this exact same thing, but I'm going to make the branch perfectly predictable. So it's just always true. With the branch, without the branch. So same code, but I just changed the branch to be always predictable. Now my branchless optimization is slightly losing. Well, not that slight, I mean, it's considerable, because I'm evaluating both expressions all the time. So before you do that, look with the profiler to see that that branch was badly mispredicted in the first place. The other thing, sometimes, even if from the source code it looks like your branch is going to be mispredicted, the compilers will actually do that optimization for you. In particular, that question colon on the return usually gets optimized. Not always, usually. What makes it worse is different compilers do different things. So I have a very short example where Clang and GCC do different optimizations. GCC makes its own branchless optimization, and you can't beat that. And Clang doesn't, and you can beat that. So you have to profile the results of your code. Sometimes very similar code that compiler did the branchless transformation, it doesn't. Those optimizations aren't very well sort of developed. I'll show you that example. Oh, okay, I have to show the end of the code. All right, that's actually that function I've shown you on the second slide. I'm calling this function. The result is, the rest of the code is exactly the same. So I'm adding the result of that function to some value, but how do I compute the return value? In one case, I say if b return like add something, and in the other case I use boolean as an integer, multiply by 0 if I don't want to change anything. Otherwise multiply by 1 if I want to add that number. Branchless costs me a little bit of extra computation. Again, this is a mispredicted branch. With the branch mispredicted, branchless optimization. Now, with the branchless optimization, I don't care if it's mispredicted or not. But if the branch was perfectly predicted, that number would be around 700. So perfectly predicted branch doesn't pay off. Mispredicted branch pays off spectacularly. Okay, let me show just, we're basically at the end. I'll caution you against one more thing, because there is a very similar optimization you can do with functions. If you don't know what you call, you may be tempted to do a jump by function pointer, which is the exact same idea as I did with the branchless optimization. Almost never works, and if those functions were inlined, it's a spectacular failure. So I'm not saying it never works, but be really careful with this, always profile it, and even then, like, if you get to a better compiler maybe that can inline, could still be a spectacular failure, so be really careful with doing that thing. Okay, so let me just restate the train of thought. The more of your computing capabilities you can use, the faster the code executes. The processors have a lot of computing capability, and usually they're waiting on data. The designers came out with a clever workaround, which is the pipelining. Detect multiple independent instruction streams and do them interleaved. Works great until you don't know what to do next, because not just the data depends on the previous data, but the code depends on the previous data. That's conditional, that's branches. They came up with a workaround for that too. Make a guess about the outcome of the condition, pick that code, and run with it. Very expensive if the guess was wrong. Now, there is no workaround for that in the processor, now it's on us. Make an optimization by replacing a non-predictable guess with a predictable guess, or removing the guess and the condition entirely. So what did we learn? Predicted branches cost you almost nothing. Mispredicted branches, terribly expensive. Optimization, use fewer of them. There is a cost to it. Don't do it unless it's confirmed, and verify that it actually works. Both are done with the profiler. Well, as I mentioned, the illustrations done by my sister-in-law and 2 more members of the family that deserve credit for allowing me to use their laptop. If you want to read a lot more about the performance in C++, including more about the branchless optimizations and what gets you there in the hardware, you can find it in my book, and that link on the bottom gives you 25% off for all the conference participants. And now let's take all the questions. Thank you.
In the more, let's say, common case in which I can both have some prediction on the things, on the booleans I'm checking, I can order them by how likely each of them will fail. And also, if they're false, usually I care less about performance, like I care more about the performance of one of the branches than the other, because that's the good path. And the bad path is throwing exception, and I'm going to pay a lot anyway. Does it make sense to do those kinds of optimizations in such a case?
Okay, so first, kind of 2 questions in it. One, if you have a composite logical expression that is sufficiently complex, it depends on how predictable each term is, and not how predictable the result is. So if you have terms that are much worse predictable than the overall result, yes, it pays off to replace short circuit with like bitwise ORs and stuff like that. Okay. When it comes to the overall expression, now, the fact that one of the branches is like emergency branch by itself doesn't matter. What matters is you'll probably rarely get there, which means once you replaced individual unpredictable terms with the overall result that is well predictable. I mean, you're not going to be throwing exceptions often. So you're basically postulating that the overall result is well predictable. At that point, you're basically done, because a well-predicted branch is cheap. You can't optimize your way around that. You just can't beat it. This is the case for which they try to optimize their processors really hard. You can't beat that.
Yeah, but as you said, I'm confusing because I'm using multiple terms.
Individual terms within the expression, if they are much less predictable than the overall result, so you say X or Y.
Yeah.
If X is poorly predictable, Y is poorly predictable, but the result is well predictable, like at least one. So let's say 60% of the time X is true, 60% of the time Y is true, but they're strongly anti-correlated. So like only there's maybe 0.1% of a chance that they're both false.
I see, but if you don't have correlation, then I can use the short circuit.
Yeah.
Okay.
Do we have, okay, let's go to the other side, we'll come back here.
You observe that... This session is over. Thank you.
Well,